Yeah. Well, it looks like it's official. Welcome back, everyone. For today's class, we're just continuing on through section 7.8. But I did want to talk about the exam. I should have this exam graded sometime over this weekend. I'm going to start grading it on Friday, but I want to clear through the grading of the homework first so that once I grade your exam, you'll have a good understanding of your course grade at that point in time. And so keep in mind, it's always a good idea to check your grades on a week-by-week basis. Anytime anything gets graded, grades get put in, but your course grade is your running tally as it changes from every single upload. So week by week, you can always take a look at how your current course grade is doing. And being pretty aware of what's in there also helps out if a mistake occurs. Maybe you did some in an assignment, there's no score in, then that's something that can get corrected right away. I'm not in a habit of making those mistakes, but nobody's perfect. That's something you should look into all of your classes. And so I'll have the exams grade over the weekends at some point starting on Friday. It's going to be a long grading set. I signed 4 exams this week, so lots to do, but we'll get through it. And we have President's Day next week, so that'll make it a little easier as well. Any questions at all, folks, then, before we get started with today's work? Okay, once exams are graded, I'll post some summary statistics here if you're curious about average maximum scores that were obtained. I think usually everyone's pretty curious about that kind of information. I'll also post the solutions as well here so you can check your work and that kind of stuff. But for the moment, we're now just continuing through the Moodle website, and pretty much everything we saw as it came up to exam 1 just keeps on getting replicated in the same exact way until we're in exam 2. Looks like that one's going to be after midterm week. It will be right before spring break, so no exam worries coming back after that break there. So here's where we left off. Well, this is the last problem we finished off in the notes in improper integrals. This one was an improper integral type 1 due to the infinity right up here. First thing we have to do for these kinds of problems, whether it's a type 1 or type 2 improper integral, is we have to do that setup there. We mentioned if this was a 10-point exam problem, the setup here with the limit statement could be as many as 2 points. Nothing major, but still important, and it can really decide the direction your problem goes. Sometimes people can forget that there is even a limit unless it's written down. So writing it down once is like a great way to help out in those kind of problems in reality for the exam. But now we're turning into improper integrals type 2. We need to know the difference between the difference ones. Think of for type 1, you have an infinity somewhere. But type 2, different thing that's going on is it's all about discontinuities now. The discontinuity is going to be for the integrand, the f of x function, relative to the domain you're integrating from a to b. Just like there's 3 different ways to break up improper integral type 1, for discontinuities, there's 3 different ways to break down your integrals as well. The red here is not because of a typo this semester. This was a typo last semester that got corrected. Let me take off the red. That's a bit of a distraction. But let's take a look at each one of these. First, we're saying f is continuous on this interval from a to b, but we have a discontinuity right at b. Whenever there's a discontinuity at b, we swap the upper limit of integration for a new variable t. The trouble is with that discontinuity, you cannot use the fundamental theorem of calculus part 2 again. You have to have a continuous function on the entire closed domain, but it's continuous on all numbers right up to b. So we take a limit as t approaches b from the left, put a new variable t right here, and we're all set. Obviously, that's tough to decide the direction though. Yeah, go ahead.
Kind of like for piecewise functions, like part of it, right now.
Not necessarily, because when it comes to a jump discontinuity, you can actually break up your integral across that jump discontinuity. This is more, you have got a vertical asymptote in the problem, kind of a discontinuity. So just for a visualization of what I was saying earlier as well is, if you have a graph that goes, say, like this, from A to B, your curve is continuous except over here, right across at C. This is continuity only from the right, since it lands on a solid dot. It's not continuous from the left whatsoever. But this one special case can actually be handled this way. Integrate from A to B, f of x dx. This will be an integral from A to C, f of x dx, plus an integral from C to B of f of x dx. And we could integrate in this kind of way as well. We would get the antiderivative, evaluate at the relative values, and be all set. Effectively, we're just finding that area going that way, and then that area going that way by breaking up the integral. But for these types of integrals, we have a bigger problem. We have something that looks more like this on the graph. Say for this one, where we had the discontinuity right at B, let's go from A to B. The discontinuity is going to be something more of these lines where we can't just run through it with this kind of trick, breaking up the integral. It might look something like this then. And the question is, very similar to the question before with improper integrals type 1. It's just that the infinity is in the vertical asymptote. The infinity is not that you're integrating on an infinite domain, but it's still a question. This goes up forever. There's still going to be area between the vertical asymptote and the curve. So we wonder, does that area converge to a finite number, or does it blow up to infinity? So still very related questions, but totally different looking graph this time. Other questions at the moment? Okay, again, another thing that's tricky is the directionality there. T has to go towards B only from the left in this kind of picture. So let's say our variable T is right here. If you integrate from A to T, let me try again on that T first. If you integrate from A to T, you're okay with the fundamental theorem of calculus because you're continuous from here to here. The discontinuity is at B. So we allow T to move in this direction, head towards B. It's heading towards it in a specific direction, only from the left. T is not on this side from the right. And as T gets closer and closer, we can use the fundamental theorem of calculus every single time. And now the question boils down to, does that limit exist as T does in fact head towards B from the left? Well, that's one type, but the discontinuity could be on the other endpoint, the lower endpoint A. If that happens, that means we're going to swap out that A value, take the limit as T tends towards A from the right, and I noticed a typo on these notes. Should have looked like this. Supposed to be an arrow, so that's the fix on that one. One day I'll find all of these little typos. So as T approaches A from the right this time, we just throw in a new variable T here for the lower limit of integration. So the way to visualize these, if the direction of where T is approaching from the left or the right seems kind of strange, you could just take this, write it out as a number line. Here's A with the discontinuity. I'll write out disc, short for discontinuity. Here's B, where you are continuous. T would be in the middle, but T is heading in that direction, towards A. We have to put a plus in there because it's heading towards it only from the right-hand side. So this picture right here is only to support that right there, the direction T is heading towards. Notice these are single-side limits each and every time. Sometimes when you do the limit, the fact that it's single-sided doesn't seem to matter. Other times it absolutely does. It just depends on the function and what's going on. So out of safety, we write these down each and every time as part of our setup, just like on the other integrals. Then if there's a discontinuity on the right, discontinuity on the left, the only way this changes is if the discontinuity is in the middle. So between A and B, if you have a discontinuity, we would take this approach right here. It doesn't work as nicely. We still have to throw a limit in there to handle that discontinuity. And it would look like this. Break across a discontinuity. So for discontinuous at C, here's our two new integrals to handle. But now T has to be replaced with C in these kinds of ways. On the first integral, here's what the visualization is going to look like. We're going from A to C, oh, hang on, going from A to B rather. We're continuous on those values, but the discontinuity is at one point C. So if we're looking at this end, T heads towards C from the left. That'd be because you are right here. T is on the left end. And when it heads towards C, we put in that negative sign to say specifically just on that side between A and C. The situation is different if T is, say, over here. That means you're integrating the C to B integral. We replace T with that limit. But this time, T is heading towards C in this direction. It's coming in only exclusively from the right-hand side, so we put a plus on that one there. We'll leave the diagram like this, just to convey how we got the plus on that one. And similar thought on getting the negative. They're not necessary to throw down these diagrams on your paper unless they're helpful. I'll put them down as well when we integrate, just to get a feel for how that strategy works. But any questions at all, folks, looking at these three new kinds of improper integrals? Okay, visually, we're just wondering if you write down a function that looks like this, say y equals 1 over x, and if you were to integrate from, say, maybe 0 to 5 or even 0 to infinity, would it converge? Those are the kinds of questions we would want to ask and answer. But notice also, you can write down an integral that's both type 1 improper because there's an infinity on it, type 2 improper because there's a discontinuity on it. These are not mutually exclusive integrals. So this one would be type 2 if we integrate from 0. 0 is a discontinuity. And you might decide to integrate off to infinity. That's also a type 1 all at the same time. We won't look into as many integrals just like that. That's a lot of stuff going on at once. But it's good to be aware you can write down just a really messed up integral, break it up as a type 1, type 2, and go from there. It could converge or diverge. Well, what we want to do next is just practice doing that for just exclusively type 2 integrals. Instructions here are basically verbatim. We're going to determine convergence, divergence. So that's just our last thing we say. Either it converged or diverged. If it did converge, we find the value it converged to. That just means we have to evaluate the limit either way. And this is a reminder that not so much I'm going to be picking on expressing every step with limit notation, but we have to at least do the setup with limit notation. So let's give this all a try. We're integrating what's usually a totally fine function, 1 over 1 minus x, but it's not fine on that domain. Anyone see what the discontinuity is for that function? Absolutely, problem's right at 1. You can't plug it in whatsoever. So we can do a small analysis that goes like this. Here's an x-axis because we're dealing with an independent variable x. We're integrating from 0 to 1. 1 is the discontinuity. Zero, we're continuous on. We would just get a positive 1. So our variable t, when we introduce the limit, would be here, and it has to go towards the discontinuity. It's going towards it from the left, so we say that this is equal to limit t approaches our discontinuity 1 from the left of the integral 0 to t. And 1 over 1 minus x could be just left directly in that form. So that's our setup of what we have to do for these kinds of problems. Again, it's not worth a ton on an exam. You could lose a couple points. On a real homework question out of a 5-point problem, you could lose 1 point. But the purpose of assigning it points to this is because it helps you stay on the right track, reminds you you're doing a limit. It just makes us be a little bit more accurate if we pay attention to those kinds of steps. Next thing we have to do is just come up with an antiderivative. This antiderivative is really fast. Let's go with a little bit of space right in the limit. There'll be a constant in front of it. T approaches 1 from the left. Antiderivative of something like that is like the antiderivative of a 1 over x. We'll get natural log, absolute value, 1 minus x. There's also a chain rule involved here. The coefficient of x is a -1. So we need to throw a -1 right over here as well to get the full antiderivative. Integrate from 0 to t, and we'll be all set. You know, it's kind of a crazy antiderivative in a way. It's not a bad idea when you do these kinds of things is to just check them out. Differentiation is never something that goes away. So let's do that right here as just a fast check. So d by dx of my total antiderivative also includes the constant, negative, the natural log, absolute value, 1 minus x. If you differentiate this way, you would get negative staying right where it is. 1 minus x goes down to the denominator. One amazing fact is the absolute values truly cancel, even if there was absolute values in the logarithm in the first place. That's kind of mysterious in a way. You have to write down the absolute value function, separate it by the two cases to show what happens there. But the absolute values drop. There's also a chain rule, though. You have to multiply by the derivative of 1 minus x. That derivative is -1, canceling that -1. So you just get 1 over 1 minus x, the original integrand. So that's a good check to do every now and then, just good practice differentiating. Tells us we're on the right track here. Now what we need to do is evaluate that limit. I'm not sure I can do this in the space I thought I had. Let's just drop that to a page and do it down here. Any questions whatsoever, folks, to this step? Okay, now that we're about there, let's see what this is going to turn into. Excuse me. We have negative. Limit t goes to 1 exclusively from the left. Inside here, we get natural log. It's absolute value 1 minus t, but t is going inside here and it's never exceeding 1. So this is always a positive quantity or non-negative quantity. If you want, you could drop the absolute value on that right there. Totally optional though. Then minus, plug in 0 here, and this is just natural logarithm of 1, which would mean this part here just goes to 0. We can sort out that limit, natural log 1 minus x, our work is going to be done. We mentioned before, well, I think on these notes actually, there's a couple graphs that we should always be ready to go with. They're things that we have to be prepared for on exams, for example. One of those graphs, let's take a look at it while we're thinking about this one. One of the graphs we need to be ready to go with are y equals e to the x graph. It's reflection negative e to the x as well. This is e to the t for the problem. These graphs are so important because if you're taking a limit as you go to infinity, all you're grabbing is a horizontal asymptote, and that's what these graphs provide. We're doing the same kind of thing here, except instead of the exponential, it's a logarithm, and instead of a horizontal asymptote, we're concerned about now a vertical asymptote. If we can sketch that out and understand that vertical asymptote, that'll evaluate the limit for us. So this is really just knowledge of the vertical asymptote of natural log. Let's say here, this is another graph we must know for exams. There's not a lot. I'm not going to throw in random stuff like tangent inverse. Those are things that you may or may not be familiar with, but we don't see a lot. E to the x and natural log x do come up enough that these are ones we should be ready to go with. So natural log x goes first an intersection right exactly at 1. Then it's an increasing function, goes off like that. Increases without bound, just very slowly. But what we've revealed is there is a vertical asymptote, equation x equals 0. It tells us a lot too. We can take a limit of let's say t goes to 0 from the right of natural log x. If you took this limit, that means you're following this going down in that direction. The output would be according to the vertical asymptote going down towards negative infinity. So the knowledge of this graph makes this limit immediate. Notice also you have to say 0 from the right. If you said this, lim t goes to 0, natural log x, we can't say much to that. This is a full-on does not exist because that's a double-sided limit, and there is no left-hand side of the natural log function. It's only a domain 0 to infinity, excluding 0. So this one had a purpose with a plus. It still doesn't exist here, but it told us more information. That one doesn't exist because it goes off to negative infinity. This one doesn't exist because it's just a nonsensical statement outright. Yeah, go ahead.
Is there a cutoff where you could consider the right or the left to equate it at 0? Is that what you're referring to?
Yeah, for this one, I was referring to right at the vertical asymptote, right exactly at 0 itself.
Like,
For equations in general, the cutoff value would usually just be the vertical asymptote if it's a type 2 improper.
the vertical asymptote was at x at 1, would your coming from the other side? Could you then coming from the left up to that point? Or could you also
Let me get the graph down so I can visualize it a little bit better with you. So we have a vertical asymptote at 1 to start. And then I think you said it's coming down like that on the left. Coming from the left going down. Gotcha.
if you would refer to it from the limits from the t approaching 1? Yeah, and then it would just be from the left, so it would be negative.
Yes, absolutely.
When you do the, like, referring to it coming from the left or the right, you kind of like figure out, is there? I think this is always where the vertical asymptote is.
Yeah, for these kinds of problems, that's pretty much how it's going to always come in. So if your curve lives towards the left of it, you have to come in from the left, and it's always going to be relative to the vertical asymptote. Reason for that is when we did this one right here, we're targeting the discontinuity, and a new discontinuity is going to come in at the same exact value when we go to do this limit. And over here, the curve only lived towards the right with a vertical asymptote, so we head right towards it, specifically to the right on that one.
Do you ever write it in this notation for other types of graphs?
Potentially, yeah. Did you have a particular graph in mind?
Does any of them that asymptote?
With no asymptote. So say graph that goes maybe something like this. No asymptote whatsoever on this one. Let's say the solid dot is at height 2, open dot's at height 3, and this occurs right at maybe 2 for no apparent reason. This time we would have to use single-sided limits because lim x goes to 2 of f of x would be a full-on does not exist whatsoever. It's directionality dependent this time. You could say lim x approaches 2 from the left of f of x. That one would have a value. You'd be getting a value of 2 on this one. And you could also say limit as x approaches 2 from the right of f of x. That means you're up here coming lower and lower to a height of 3. But then limit as x approaches 2 doesn't exist because there's 2 competing values now in this case. That's what causes that it does not exist on this one. Does that make sense with that sort of graph there? Awesome. Thanks for asking those questions because these sort of things with limits, really easy to forget. It seems like calculus starts with limits, picks it up a little bit with L'Hopital's rule, and then forgets about it. But it all comes right back in calculus 2, a little bit in calculus 3 again. So these are good things to review. Other questions at the moment, thinking of these graphs and those associated limits? Or any other questions at the moment? Okay, Now that we have that graph, notice how this feels a little bit different. But when you're looking at this, you're heading towards 1, specifically from the left. When that happens, the values inside natural logarithm are getting smaller and smaller. That means you're inputting values that are smaller and smaller inside natural log x. We're getting negative infinity on this part right here. Natural log 1 goes to 0, so this turns into negative. Limit on this is negative infinity. We have to be really careful and mindful of doing any kind of arithmetic with negative signs when infinities come up, because oftentimes you might be looking at indeterminate forms. But in this context, it would be just an ordinary infinity with double negation, which means the original integral, this one way up here, diverges. I think we'll have some convergence on these, but the divergence of this one, let's see if we can see it just by putting out a graph. We're integrating from 0 to 1, so we'll go y equals 1 over 1 minus x, 0 less than or equals x, less than or equals 1. This is our whole graph that we were considering. That's kind of an odd graph. It goes up quite aggressively upwards. But from 0 to 1, this is saying the area blows up to infinity. Looks like that makes sense. It's such a steep, steep graph. Small changes in the x-coordinates, you get, that actually breaks down, and that's not going to give me values beyond 9.33, but it's blowing up so rapidly, we aren't getting any finite area on this one. But any last questions, folks, on getting through this one here? Okay, well, let's give this next one a try then. So we had a discontinuity on the upper limit of integration. Part B has a discontinuity on lower limit of integration. Same graph that we're looking up above there on the notes is relative to this one. So vertical asymptote occurs right at 0. So the number line analysis on this one to get the limit set up would look like this. We have discontinuity right at 0. There's nothing to the left of 0 since we're looking at the natural logarithm function. But everything to the right of 0 is continuous, so all the way up to e. We'll have a variable t in this range, but to get a feel for the original integral, we take a limit as t approaches 0, but this time from the right-hand side of 0. That looks like a backward 6. Let me fix that. So that informs us that over here, we're now looking at the limit. T approaches the discontinuity, 0 from the right, of t up to e, natural log x, dx. At this stage, we're all set. We just need an antiderivative, take the limit, and we're all complete with this one. Any questions first to this stage? Well, the problem with the graph of natural log x is right at 0 itself. So its graph looks like this pretty much. Here's 1, 2, 3. E is right at that value. Graph looks, oh, hang on, let me draw it a little bit better. Graph looks about like that. So here's y equals natural log x, the total graph. But on the domain, if we're integrating from 0 off to e, the discontinuity is right over here. So we always head towards that discontinuity. Other questions at the moment? Okay, well, I guess I have a question. Anyone recall the antiderivative of natural log x? This is one that's applied to us on exams because we're not meant to rederive it through integration by parts each and every time. Anyone happen to know? Yeah, exactly. So we'll just say here, drop that in. That was actually provided on the last page of the exam as well. Our author shows that as an example integration by parts. So it's one that you can always just take for granted. This is limit. T approaches 0 from the right of x, natural log x, minus x. Whole thing is evaluated from t up to e. So let's plug these in. limit t goes to 0 from the right of, plugging in an e first gives us e natural log e minus e. But the natural logarithm of the e is 1. Let's actually say that on the graph. Here's e. That would output directly to a 1. So this is just e minus e right here. The whole thing is going to cancel. Then next, we're just plugging t in. So t, natural log t minus t. And that's our entire limit statement we have to take and compute. But again, this is just gone since natural log e is 1. So we have limit t goes to 0 from the right. This part is a little bit scary, I'd say, so let's be careful with that. Maybe let's take one more step and rewrite this as negative t natural log t plus t. This one again has some concerns because if you go to 0 from the right on this, you have indeterminate right here. It's indeterminate. A form, well, it'd be 0 from here if t goes to 0, whether it's from the left or the right, that's just going to go to 0. By natural log t, as you go from 0 to the right, you're plummeting downwards towards a negative infinity. And that gives us an indeterminate on this one. But good news is the other parts right here, that goes to 0 in the limit. So we can just wipe that out. I usually put little arrows to say that went to 0 in the limit as a kind of cancellation with an explanation as well. So that means all of our work is going to boil down to, let's take the constant -1, put it in front. Limit t goes to 0 from the right of t natural log t. At this point, we're just using L'Hopital's rule to do the analysis on this one. In L'Hopital's rule, we can't work with that indeterminate form. We need 0 over 0 or an infinity over an infinity. Easiest thing to do then is to send one variable downwards. Sending natural log down is probably not a good idea because the function is more complicated. You need a chain rule now. But sending a variable t down to the denominator is usually not too much trouble. So in this kind of configuration, that's usually a better advice. This would turn into negative limit t goes to 0 from the right of natural log t. The denominator is just going to be t power -1. Or 1 over t if you prefer. And the graph of 1 over t would give us, for this form, well, still, in the numerator, we're still going from 0 from the right. So it'd be of type negative infinity in the numerator. But for t power -1, when you go to 0 from the right, you're getting larger and larger positive values. That one's just blowing up to positive infinity. This is good. This means we can now use L'Hopital's rule. So L'Hopital's rule can now be used. Well, this is our second look at it. Any questions before we run through another L'Hopital rule problem, essentially? Okay, L'Hopital's rule, again, it's kind of exciting because you're not doing a nasty derivative on this thing. You're just differentiating the numerator and the denominator independently of one another. So there'll be negative t goes to 0 from the right. Derivative of natural log t is 1 over t, but you could call that just t power -1 as well. That is a 1 over t. This derivative gives us negative t power -2. That means our negative signs are going to cancel off. And we could revisualize this in a better way by forcing exponents positive. It's limit t goes to 0, t power -2 gets promoted up to the numerator that way with a positive exponent. T power -1 is just a 1 over t, goes to the denominator. And I dropped something along the way. This is limit as we go to 0 from the right. There we go. From the right and the right. And now limit t goes to 0 from the right of just t. Going to 0 from the right was important because the limit would not have made any sense without it. But once we went to L'Hopital's rule and the natural logarithm disappeared, Going to 0 from the right had less meaning because these are double-sided limits that would have existed in either case. So this is a time where we had to be extra careful, but it didn't matter as much on the end. Sometimes it makes all of the difference, like on the prior problem. This is just 0. Weird, right? That means the whole thing converges. And the value it converges to, as t does get closer and closer to a 0, is exactly 0 on this. The only way to make sense of that is part of the graph has to be above the x-axis, part of it has to be below. That's about what we're looking at right here. And it's also telling us that this area and this area that goes down forever, they are exactly the same with opposite signs. That's kind of weird in a way. So from here to E is exactly the same area as this. It just gets assigned a negative sign whenever we use the definite integral. But any other questions so far, folks, with this one here? Okay, definitely bizarre kind of problems. Oh, I see a chat I missed. Sorry about that, Jose. Jose says, so we figured out that the 0 is discontinuous by graphing the function. Yes, by knowing the graph of natural log x, we would know that there's a discontinuity because of that vertical asymptote right there. So really there's two graphs we just have to be aware of because of the vertical asymptote giving us a limit or the horizontal asymptote giving us a limit. It's the natural log x graph as well as the e to the x graph, the one that's up there above in the notes. Other questions so far? Okay, well, let's keep on going. Let's try out the next one then. Part C is going to be the last one for these notes. We're integrating this time from 0 to 2. So our number line analysis goes pretty much the same as before. Another x-axis to match the variable. Lower limit of 0, upper limit of 2. If you plug 0 inside here, well, that gives you a value. This function is continuous at 0. It's also continuous at 2. Might not look improper, but if you spot a discontinuity, looks like a lot of people are saying 1 is the discontinuity, then that's the problem with this one. This is type 2 improper because right here at 1, we've got a big problem. That's our discontinuity. It's a vertical discontinuity as before, vertical asymptote rather. So that's our discontinuity, which means we'll have to break up our integral from 0, 1, and 2. So let's make that our very first step on this one. The original integral is improper. The next integrals are also going to be improper, but we get to handle them one integral at a time. So we'll go from 0 to 1. I'll rewrite the integrand as x minus 1 power negative 3, just an easier antiderivative for me to visualize. Then integrate from 1 to 2, x minus 1 power negative 3 dx. And we have two integrals to take a look at. It's the same sort of situation we saw if this was improper type 1, where it went from negative infinity to positive infinity. If one of these diverges, the whole original integral is divergent. But it's actually kind of hard to pick which one is going to diverge and which one's going to converge. I probably would just try one and see what happens going left to right. So the strategy at this time is, if you're really up to it, you can just handle two limits at once across a plus sign. Or if you would like to divide it up, call your first integral I1, your second integral I2, and we'll just do these as chunks. Let's try out that strategy because it's, I think, easier to actually read as you write this all out. So splitting this up, first look is at I1. We're integrating from 0 to 1, so that means for I1, our variable t is right here in the middle. It always heads towards the discontinuity, so we'll say limit t heads towards 1, but it's heading towards 1 exclusively from the lower end, from the left. So we put in that negative sign there. And now we integrate from 0 to t. X minus 1 power negative 3 dx. So if we can find the antiderivative and take the limit, our work might either be complete if it diverges, halfway complete if it converges. If it converges, we need to take a look into I2. Any questions at all, folks, with this setup so far? Okay, well, antiderivative is pretty fast on this one. We can write out that this is equal to, give it a little bit of space so we can throw a constant in front of that. T heads towards 1 from the left. It's x minus 1 to a higher power, -2. We have to multiply by the reciprocal of that power, so -1/2 in front. Then evaluate all of this from 0 to t. So next line, we have -1/2 times the limit. As t heads towards 1 from the left, when we plug t in here first, it's t minus 1 to power -2. Or if you prefer, that's the same as 1 over t minus 1 squared. So I did two things in here. I plugged in t for x. I made that a positive power so that we have power 2 in the denominator. Then go minus. This time plugging in a 0 is just going to give us -1 to power -2. Well, that's really just a +1 altogether. So that's our limit to take a look at. And as we look at this limit, we're heading towards 1 from the left of 1 minus 1 divided by t minus 1 squared. This has a vertical asymptote right directly at t. We can say, just as a related concept, the limit as t goes to 0 of just a more simpler kind of problem, say 1 over t squared, this would be equal to infinity. Does that make sense to folks on that limit there? Seeing it graphically, essentially, or not quite graphically, but seeing it numerically, essentially what we're saying is we're taking 1 over something small squared. So it would start up like this, but then it would become, say, 0.1 squared or 0.01 squared. As it gets smaller and smaller heading towards that limit, the values get to larger and larger. So that's our indication. Limit goes off to positive infinity on this one. The positive infinity is also because of the power 2 on this as well. So down below here, as t heads towards 1, this denominator is getting closer and closer to 0, much like over here. This whole thing is blowing up towards positive infinity. Okay, multiplied by a negative sign in front, that means it's going off to negative infinity altogether on this one. We can say since lim t heads towards 1 from the left of 1 over t minus 1 squared, that itself is heading towards positive infinity. So same concept as above, just a small change of what's inside here versus the limit. So 1 coming in from the left, this one's kind of weird because whether it came in from the left or the right, the power 2 is still going to take what's a negative number, convert it to a large positive one. If it was power 3, though, we would have to be very, very careful with that. Now we'd have to wonder, is it negative or positive infinity with an odd power? So we had positive infinity here, multiplied by a negative constant. This subtract 1 has no bearing on the problem now, that one part headed towards infinity. So due to that infinity, we can say diverges. If you left your problem right here, I wouldn't be super picky, but we are only saying this diverges. Our real conclusion should be that this diverges up here. So let's say as one overall large conclusion, therefore, the original integral from 0 to 2, 1 over x minus 1 cubed dx must diverge. Must is a very strong word, but that's the concept here. If one part fails to converge, the whole thing is divergent altogether. But any last questions, folks, on surviving this one here? Okay, well, that's our run through with improper integrals. I would say improper integrals type 2 are the more technical one because of the directionality and the limit coming into the picture often, well, essentially always on these. But improper integrals type 1, they come up a lot in our course. We're going to see them when we're in chapter 11. Think of this as something that is still important, but it's more of its kind of its own topic as far as this class is concerned. But congratulations is definitely in order for a second reason. We just survived chapter 7. That's sometimes the hardest part of calculus too, because hitting the ground running with integration is not always easy. It gets a little bit easier in chapters 8, 9, and chapter 10. And then it gets hard to get into chapter 11, but we'll all get through it. Chapter 11 is about a third of this class. It's not necessarily anything that makes or breaks us, but it is a rough spot that we have to get through. It sequences in series, yeah, exactly. Because sequences in series are so touchy, you might have noticed something odd on the syllabus. In our day-by-day syllabus, we're actually doing chapter 10 last, as weird as that sounds. It's weird to reorganize the chapters of the book. That's because you never would want to do, say, 11.10, Taylor series, Maclaurin series, on the last week of the class, essentially. That's really hard to absorb that at that point. So instead, chapter 10 is the lighter topics. You don't necessarily want to ever omit something as kind of filler-like, but that's what chapter 10 is. It's important. It's not the most important thing, but we end on chapter 10 also because it connects really well with calculus 3 when you're dealing with multiple variables. That's about pretty much what's going on in that chapter there. But for the moment, let's open up our chapter 8. Here we're looking into applications of what we are doing in chapter 7. Our first application of the day is going to be arc length, finding just the length of a curve. Imagine we've done that all the time, right? We have formulas for it. If you write down a circle, that's an interesting curve. It takes really two functions to draw that. But you can find the length by just saying circumference is twice pi radius. So we're extending that idea to other kinds of functions, like say a function that could be drawn out like this. If we can find the length of that curve, it could be a really, really meaningful physical quantity. For example, if this is a particle in some kind of Large Hadron Collider type situation, this could represent the path it takes. We can then calculate the distance it takes, its speed it's going, all sorts of interesting things, all through arc length. But the first thing we have to do here is, well, this is a real application of integration. Applications of integration are kind of funny because they go like this, really. Let's go all the way back to the definite integral. An application of integration often means you have some physical problem that you want to solve. Finding the length of the curve is what we're doing in 8.1. If you can get the Riemann sum into your problem, now you have an application to the integration because it transfers into an integral in this way. So our objective at the start of these notes is to show how this can come into play for us in the process of getting the arc length. So let's just park it down here for a quick reminder once we get there. And this will be our third derivation for the course. We did 2 in chapter 7, integration by parts, and the 1 for trapezoid rule that didn't quite work out the first time. Sorry about that. This time I have a cheat sheet, so I'll try to stay right on the rails and not look at it too often. But really, you don't need a cheat sheet to start this off. Let's first just go through the definition. We have a curve C defined by a function y equals f of x. Let's just draw that out. It's going to be continuous from A to B. I'll draw everything in quadrant 1 just to minimize distractions. So here's the A. Here's the B. The function, I'll plot in this kind of way. Here's y equals f of x. So we start with the curve. There it is, a nice continuous curve from A to B. And the next thing we want to do if we want to find the length of this curve is we're just going to estimate. And one really good estimate already is, well, I said good, but it's a, back of the envelope ballpark estimate. You can find the distance of a straight line, no problem, right? If you want a better estimate, you can find the distance of this line, the distance of this line, and now it's somehow doing a lot better. And that's where the Riemann sum is coming into play. If we can state this just right, we'll get the formula for arc length. So instead of drawing a bunch of random lines, let's go to the next part. We're in an application for integration when we do these next steps for sure. We can divide up the integral from A to B. into n subintervals with this equal width, delta x. So we'll say A is x naught. This value would be x1, x2, x3, and B is x4. So this is just a picture when n equals 4. Again, because it's a derivation, this is not really a problem I'm going to ask you to do on exam. This is more just an opportunity for us to look into old things like these formulas are really, really important. They never go away. And other things like the mean value theorem enters into this picture in the most random way as well. So we'll review that as we go along with this. So you have the partition down below. Now the curve C can be approximated by finding the distances among these points. P naught, X naught, Y naught would be this point, P naught. X naught is the first coordinate, Y naught is the second coordinate. When you see a Y naught, also think of Y naught is just f of X naught. So just compressing the function notation essentially. So there's P naught at that point. Up here, directly up, is P1. Then directly up from here, P2, P3, and the last one is P4. So this is again picture with just n equals 4. We're going to approximate by finding the distances of these line segments. So visually, we want the distance here to here, here to here, here to here. It's kind of hard to see on these smaller segments. When the curve changes its height, its variation a lot, it's easy to see the difference between the two. When the curve gets flat, they seem to do a pretty good job of matching up with each other. Now, if we look at just one distance, say this one, we often express it this way. P naught, P1, absolute value bars are just saying the distance from P naught to P1. That would be equal to the square root of the difference in the coordinates for x, x naught and x1, and the difference in the coordinates for y, y naught and y1. So oftentimes we write this in by going x1 minus x naught squared plus y1 minus y naught squared. So that would just be one distance. But already there's an interesting substitution you can make right here. Anyone happen to see what a substitution could be? Kind of weird, but if you put delta x right there, that would actually be right in a certain sense. Notice how weird it really looks though, because delta x is this quantity. It's the width of each one of these intervals right here. So if you say x1 minus x naught, that's a negative value, but the squaring is going to just peel off that negative sign immediately. It has no meaning at this point. That's really just delta x squared. So you can put in here that this is equal to root delta x squared plus y1 minus y naught squared. And then that's getting us closer to the key, because if we're going to write down a limit of a Riemann sum, delta x has to show up some way somehow. So the fact that it did is great. Let me put that squared in a more sensible way. But if I can't get it outside of the square rooting function, notice it's outside of any f function here, we still have a problem. So that needs to factor out some way somehow. And that can never happen unless delta x also appears right here somehow. That's weird, right? You can get delta x going this way, but how do you get a delta x going this way is the next struggle in all this. But any questions at the moment with where we're at? Okay, here's where we need to actually make a pretty big assumption. We're going to put a delta x there one way or another, but this is the assumption we want to make. Mean value theorem is coming into play, which means the function that's going to emerge somewhere inside here will involve the derivative. Or that means we're trying to integrate something involving the first derivative, and the only guarantee that that integral exists is if the derivative is continuous from A to B. So that's going to be our big assumption right here. We'll say, assume f prime of x is continuous on the interval from A to B. That means it would be continuous on this interval here as well, with continuous from the right on one endpoint, continuous from the left on the other endpoint. But continuity here of the derivative gives us even more. Mean value theorem is now on the table, so let's recall exactly how that goes. So aside from the definite integral, mean value theorem is another thing that just never goes away. And right here we need it, because without delta x, there is no hope of turning this into a Riemann sum whatsoever. So here's the review of the mean value theorem out of nowhere. The mean value theorem says we have to have a function that satisfies all of these hypotheses. The function has to be continuous on the interval. It has to be differentiable on the interval. And if we assume that the derivative is continuous on the interval, it hits both of these all at once. We have differentiability. Well, looking at the derivative. If the derivative exists, then the function itself is continuous. So we're on okay track for the hypotheses of the mean value theorem. Here's the actual assumption, or excuse me, the conclusion. There will exist a number C between A and B. The A and B in our problem are this value up to x1, because we're only looking from P0 to P1. So the mean value theorem says some number between here. We call it C down in the theorem, but we'll call it x star when we go to write it out. So that the derivative of f at x star will equal these quantities. Let's drop this into our paper and then just work with it with the values that we actually have here. So this is the conclusion of the mean value theorem, and we can now say by the mean value theorem, we're doing the mean value theorem only relative on that one little interval. Well, it's going to be applied to every single one of them, but we're just showing how one of them is going to go. So next, by the mean value theorem, there exists xi star in the open interval containing a, which is x naught, to the next value, x1, such that now this xi star right here is going to go right inside that f function, or this equation is a little bit more beneficial for us. Let's put it right inside here. The b is going to be x1. The a is going to be x naught. That c right we have right there, that's going to be the xi star. And same values that go here, that would just be at x1, x naught. So that's what the mean value theorem is saying so far. But when you look at this really, really closely, x1 going in here, that's just y1. y1 is equal to f at x1, in other words. So this would become y1 minus f of x naught, that's just y naught. It'll be equal to the derivative of f at xi star, and we still have to do something with b minus a because I don't have a delta x emerging. Well, what's b minus a? Exactly, in our problem, b is a, or excuse me, yeah, that's weird to say. B is this value x naught, that's better said. A is the upper, hang on, b is x1, a is x naught, and so this distance is, like you said, just delta x again. We can plug that way back up here and now assert Because of the mean value theorem, therefore, the distance from P naught to P1, this also extends to the distance between any one of those points, is now the square root of, we got 1 delta x squared to emerge right here. Add to that the yi minus y naught squared is this. We're just putting a power 2 on it. So that f function will have power 2. F of x1 star squared. And delta x itself will also have power 2 since we're squaring that entire line down there. So delta x squared as well. Because delta x has appeared in 2 spots to power 2, think of the same kind of thing when we're doing trigonometric substitution, when we factor out square root of 4 or something along those lines. Here we can factor out delta x. So this turns into root 1 plus f x1 star squared times delta x. Delta x gets square rooted, so now it's back down to power 1 way below here. So that's finding the distance once, but again, this can be generalized. And with n equals 4, we have a pretty great approximation. We want to do even better. We want our approximation to get better and better until it's the true length of the curve as we'll define it. So we'll put a limit in front of our statements as we go to sum them up. So if we continue on this, it's nearly done. Here's the punchline. We can say that the length or arc length, I'll just say simply length, is going to be the limit as those number of intervals go to infinity of the summation, I goes from 1 to n, of the distances, pi minus 1 to pi, generalizing just the first line segment that we wrote out. But this value now has an expression. We can say this is limit as n goes to infinity, summation as I goes from 1 to n. Over here by the red dot, it's not a Riemann sum until you can get a delta x out, and that's what we showed is possible. We get that this whole thing, generalized from the lines above, is now root 1 plus f of x1, I, star squared, multiplying delta x. And at this stage, it is a Riemann sum. Let's pull down that part right there. This was our major objective, to get a Riemann sum into the picture. And it didn't have to be arc length. This can be just about any physical process that can be broken down into small pieces, turned into a Riemann sum. To the author that wrote this book, that is, in his opinion, the major application of the definite integral, either way you look at it. But we also want a formula, so when we go to actually find arc lengths, we're going to be using the formula that we get right here. Here's how it goes. Notice that the limit gets replaced with the integral sign. We integrate from a to b, same a and b that was up there on the graph. Next thing that happens is xi star just turns into an x. But this is the entire integrand. It comes from whatever is here. Our integrand is then root 1 plus just f of x squared. So no xi's anymore. And the next thing that's weird that happens is the delta x just turns into a dx. So full swap right here. And that's our formula. Oh, one thing I forgot. Looks like I forgot a lot. It should have been a prime. Yeah, let me put in that correction there. Yeah, should have been prime there, there. Oh, geez. Here and there, finally. Thanks for spotting that, prime.
Area.
Absolutely. What we're going to do for surface areas is take that whole curve, rotate about either axis, which involves including a 2 pi, a right extra function inside of there, and this as well. Absolutely. Well, we did it, folks. That's what the derivation looks like on that. Our goal next is just to apply it. I'm not sure if we're gonna get through a problem in the 3 minutes we have, but any questions at all, folks, on getting through just the derivation itself? Okay, big takeaways are here mainly, it's always important to see how this process works when you partition an interval. And the mean value theorem is one of those weird sneaky theorems that can just show up in the most random places. This is one of those places. In fact, the mean value theorem is used to prove the fundamental theorem of calculus part 1, I believe. So it's just in everything in calculus. Well, when we come back on Thursday, we're going to take on these problems down below. And this is basically the formula that we derived with a prime thrown in. Well, any last questions, folks, before we call it a night? Okay, well, have a great night, everyone. I'll see you all on Thursday's class.
I got so long. I got so long with that explanation, and then I got really, and then I think, oh, yeah. Well, then we still don't have the actual.
Yeah.
Like, wait a minute. Like, April. Oh, yeah, she looks here. Yeah, humans really there, like water, maybe that is helpful.